Welcome back to the ChemDoctor, and this is going to be the third video that I've produced in the area of the gas laws, and specifically in this particular problem we're going to be focused on one of the four empirical laws. And before I tell you which law that is, what I prefer to do is we'll read the problem and we'll see how to set these kinds of problems up, and then we'll evaluate what variables are changing, what things are constant, and then we'll talk about which of the empirical laws that this is focused on. Now, the problem at hand is the following. We have a scuba diver, and this particular diver is planning to dive and swim into a cave. The diver is carrying on their back an aluminum cylinder that has 77.4 cubic feet of gas in it. Specifically, the gas is air. Before breathing the tank, the moles or the particles, the amount of air in the tank is constant. The temperature on the shore before the diver enters the water is 80 degrees Fahrenheit, and the pressure in the tank is 3,000 psi. All right, now the diver is going to move into the water where the water temperature is 51 degrees Fahrenheit. And what we're interested in is calculating the new pressure of the gas. This is actually a very real problem for technical divers, because oftentimes my students will ask me, because I happen to be a cave diver, how do you know that you're not going to run out of gas when you go into the cave? And the whole point is that you've got to plan your dive so that when you go into the cave and come out of the cave, you know that you have not only enough gas to get in and out, but you also carry enough gas so that if there is an emergency, that you still have enough air in order to come back to the entrance of the cave and actually get to the surface. Now, as is often the case, usually the air temperature on the surface where you put your gear on and the temperature of the water is different, and usually there is a cooling effect. And so involved in planning how much gas you need in order to go on a scuba dive, you need to recognize the fact that once you enter the water, the pressure of the gas in the tank is actually going to be decreased from what it was on the shore. So we're actually looking at a very real problem. When a diver enters the water, they usually have to recalculate their pressure. And so we're going to look at and see how we set up a problem like this and what we do to calculate the pressure. So the first thing I'm going to do, and I highly recommend this for any kind of gas law problem that you work, is we're going to draw pictures that represent the scenario. So I'm going to start by drawing a picture of a tank. All right, and I'm going to put in our initial information here. So we're going to call this state number 1. So this represents the tank of air when it's sitting on the surface prior to going into the water. All right, and I'm going to designate my initial pressure as P1, and I'm going to write down what they told us in the problem. So we've got 3,000 psi of pressure in the tank on the surface before we enter the water, and the initial temperature, which I might add is inconvenient because they've given us the temperature in Fahrenheit. But the reason that I structured the problem this way is because, generally speaking, in the United States here anyway, usually temperatures are read in Fahrenheit. Now, if you happen to be in Mexico or in Europe, then the temperature that you're going to read on your computer or by a weather report is going to be most likely in degrees centigrade, which is actually a more convenient temperature to deal with because the conversion factors are easier. All right, now I just want to remind the viewer that the moles here are fixed because we're not in a situation here where the diver will have actually breathed off the tank yet. And we're going to leave it that way. So we're going to enter the water, and we're not going to allow the diver to breathe off of the tank. That way it makes the problem easier because You don't have to worry about the fact that some of the air would have been used. And then the volume here is also fixed at 77.4 cubic feet, which happens to be the standard volume of gas in an aluminum cylinder. Now, what we're going to do is change our state. So the diver's going to throw the tank onto their back, which actually, truth of the matter is a simplification of this thing, but we'll just say the diver's going to throw this onto their back and they go into the water. So we're going to have state number 2. And in the water, the pressure is going to change. The pressure of the gas inside the tank is going to change because we're moving into a medium which is cooler than the surface. And we see that the temperature of the water where we take the tank is 51 degrees centigrade, which is significantly cooler in terms of the temperature than the surface temperature. 51 degree water is pretty cold for a diver. You're going to be wearing a heavy wetsuit and gloves and so on. It's fairly chilly. And so when you immerse that tank into that water, the kinetic energy of the gas is going to be decreased inside the tank. All right. So the temperature, because the temperature here is being reduced. So in other words, we're going to take the tank and we're actually going to cool it. And when you do that, the kinetic energy of the gas is going to go down. All right. And kinetic energy is the energy of motion. So maybe I'll actually put that in here. So the kinetic energy will be decreased. And when you decrease the kinetic energy of a gas, the average speed of the particles is going to go down. And when the average speed of the particles goes down, the average number of collisions with the sidewall of the tanks with the tank is going to decrease, which means that your pressure is going to be decreased inside here because the collisions that are happening on the inside of the tank are exerting a force on the inside of the tank. And the exertion of force is what causes the origin of pressure, right? So you need to remember from the basic instruction that you would have received either from the professor or from your teacher in an AP course or high school course, is that pressure is equal to force divided by unit area. So the pressure inside the tank is going to decrease when you cool the gas. All right. Now, let's go ahead and set the problem up. So remember again that the moles are constant and your volume is constant. All right, so the steel canister is not changing any, and we're not going to allow the diver to breathe off the tank yet. So the number of particles in here in this particular problem will remain constant. All right, so now let's figure out how we're going to solve this problem. So if we look at the ideal gas law, PV is equal to nRT. All right, and what I'm going to do is go ahead and put an asterisk above the things that are going to remain constant. So we've got the volume is constant, the moles are constant, and the gas constant is not changing. It's a constant as well. All right, and we see that the only things that are changing are the pressure of the gas and the temperature of the gas. All right, and maybe I'll further designate these with arrows. So we're going to use algebra to rearrange this formula. And when we do, so what we're going to do is we're going to divide, maybe I'll do this in steps. We're going to divide both sides by V. So then we're going to have the pressure will be equal to NR over V times T. And then we're going to also divide both sides by 1 over the T. So we're going to divide both sides by T. And when we do this, we end up with a new formula where P over T is equal to the constants all on one side of our formula. So I'll put a parentheses around these. These are constant. And you see, therefore, that in this particular gas, as we go from state number 1 to state number 2, that the only things that are changing are pressure and temperature. And this is a type of gas that in some textbooks is called Gay-Lussac's gas or Amontons Law. And it relates the pressure and temperature of a gas where the moles and the volume are being held constant. And we can write the general equation for this, where P1 over T1 is equal to P2 over T2. And the reason we can do that is because P1 over T1 is equal to these constants, which is also equal to the same set of variables for state number 2. Now, in order to solve the problem, we want to know what the final pressure is going to be. So let's go ahead and do the algebra for that. So I'm going to have P2 over T2. I'm going to rewrite my equation so the variable that I want is on the left side. And then we're going to multiply both sides times T2. So the final equation will be P2 is equal to P1 times T2 over T1. Now, when we look at the variables that we've been given, we have a problem because the temperatures were given to us in Fahrenheit. And we cannot use Fahrenheit in a gas equation. In fact, preferably, I prefer my students only to use Kelvin, because the gas laws and the behavior of a gas is based on absolute temperature. So what we're going to do is go ahead and change the Fahrenheit here first to degrees centigrade, and then we're going to go ahead and take it all the way to Kelvin. So the basic relationship we need to go from Fahrenheit to degrees centigrade is the following. I'm going to put it down here. So degrees Fahrenheit is equal to 1.8 degrees centigrade. Excuse me. It's going to be 1.8 times the degrees centigrade plus 32. Alright, so if we solve this equation for degrees centigrade, then degrees C is going to be equal to the degrees Fahrenheit minus 32 over 1.8. So using this formula, we can change the 80 degree Fahrenheit to 26.7 degrees centigrade. And what I suggest the viewer does is just pause the video and run the calculation yourself. Alright, and then over here for the 51 degrees Fahrenheit, that will work out to degrees centigrade, which is going to be 10.6 degrees C. Now, to get to Kelvin, it's an easier transition where K is going to be equal to whatever the degrees centigrade are plus 273. Alright, so for our initial gas at 80 degrees Fahrenheit, the Kelvin is going to be 300 K. And for the gas which is at 51 degrees Fahrenheit, the Kelvin is going to be 284 K. Alright, now let's go ahead and solve the problem for the change in the pressure. So P2, the final pressure of my tank once the diver enters the water, is going to be equal to P1, which is 3,000 psi. Alright, times T2, which is 284 Kelvin. And this is going to be divided by the initial temperature, which was 300 K. And you can see nicely here that the kelvins cancel out, and we have successfully solved for the PSIs, which turn out to be 2,840 PSI. Okay, now you can see that the pressure has been decreased significantly. For a diver, it's nearly, it's a couple hundred PSI, and that's a big deal. And what the diver would do, to finish my video, what the diver is actually going to do is round this down to be on the conservative side. Alright, so what the diver would say is that, okay, I've got 2,800 PSI available to do this dive, and then they would do any planning that they need to do at that stage, which actually involves a few calculations. They would do it off using this number. Alright, so this is a good practical example of how this works. And with that, I'm going to go ahead and close the video.